Good evening, Doctor. My name is Chu Jiesheng. Today I want to present about the COA project part 2, which is running a CPU benchmark program by using the assembly code. And so first we move to the data segment. We want to initialize 4 coefficients. We just follow the day of the birthday for our teammate. So the first coefficient is actually my birthday, and then the coefficient 2 until coefficient 4 is the birthday for my teammate. And then for this program, I choose the coefficient f3 as the delay factor. We want to show more obviously for the result, because if you don't use the delay factor, the result cannot see. Yeah, our computer run very fast, and then we cannot see the result. And then this all the message actually we want to display at the output terminal later. And then capture start, actually we want to record the starting time for our program. Capture end is we want to record the ending time for our program. And then time elapsed, we want to store the time progress, which is the capture end minus the capture start. And then sum, we want to store all of the y for each loop, and then sum all of the y, and then store in the sum. And then choice is used to prompt the user. If the user want to do it again, they choose the yes. If you don't want, just choose the no and terminate the program. And then we move to the code segment. First, we want to display a welcome message, and then the equation message. So what is the welcome message? It's just like the welcome to the CPU benchmark program. And then equation message, we want to show the equation first. So for this program, our equation is y equals to ax cubed plus bx squared plus cx plus d. So a is the coefficient 1, b is the coefficient 2, c is the coefficient 3, and then d is the coefficient 4. And then we just simply display all of the coefficient 1, 2, 3, and 4. After that, we want to display, we use the millisecond for each of the coefficient. So we display all of the coefficient. And then first, we want to prompt the user to enter the number of loop. Because for this program, we actually have a lot of number of loop that we want to test. So first we have the 50, 100, 200, 500, 700, and 1000. So first we want to prompt the user to input the n, and then we read the n that's stored in the EAX. Later, we store the number of n into the ECX. We all know that ECX is the loop counter. So later we want to do the comparison. If the ESI is equal to ECX, and we terminate the loop. If lower than or smaller than the ECX, so we jump to a loop and do the loop again. So first we want to store the EAX and ECX first, and then we display the progress message. So what is the progress message? Actually, progress message is like the CPU time stress test is in progress. We want to show the computer is running. It start to calculate the sum. And then first we initialize the sum equal to 0, and then we want to record the start time. So we call the get m seconds. Actually, we want to record the now for example now time is the 8 o'clock. So it will get the 8 o'clock and then convert into the binary code and then store in the capture start. Because we call the get m second, it actually first it will store in the EAX. But we want to store this as a variable, right? So we move the EAX into a capture start to store the starting time. So first we want to, the main logic is here. We move the 1 into the ESI because actually we want to plus all of the loop from 1 until the end. So the first we want to move the 1 into the ESI. So start the loop. We compare ESI with the ECX. Previously, we store the ECX as the end, right? So when the ESI1 is less than the EAX, it will jump to the it will not jump to the loop end. If ESI is equal to or bigger than the EAX, it will jump to a loop end. So first, it will not jump to a loop end, right? So it will move to the next instruction, which is the move ESI to EAX. So actually here, this segment you want to simply multiply the A x cube. and then we store the AX cube into the EDI. Later, this statement will calculate the BX square, we add the BX square into the AX cube. So we add the EDI, EAX. So we do the same as here. We multiply the CX. Since we choose the coefficient F3 as the delay factor, so we move the coefficient F3 into the EAX, and then we call the delay. We want to see the result more obviously because we don't use the delay factor, it's very fast, and then we use same the starting time and the ending time is the same value. So this no the elapsed time is 0, so we cannot see the result. So we want to use the delay factor, means that we delay. Since we choose the coefficient F3 as a delay factor and coefficient F3 is 21, so we delay 21 milliseconds for each iterator, for each loop, we delay 21 milliseconds. And then since the EAX is the CX, so we add the CX into EDI. So actually at here, and then we coefficient F4D we add to the EDI. So after this instruction, actually we have already have the Y value, which is the AX cube plus BX square plus CX plus D. We already have, and then we want to put in the sum. So we just put the sum into a EAX, okay? Because it's a sum plus equal to Y, means that we sum equals to sum plus Y. So we put the sum into a EAX, and then we add the EDI, the value that calculated previously, we add to the EAX, and then we put the EAX into a sum. So it will, this segment actually is want to update some value for each loop. Continue to update the sum value, and then we increment 1 for ECI. So first we ECI is 1, right? So we increment 1 become 2, and then we jump to a loop start. So it will back here, and then we convert ECI to ECX. So it will do the loop until the ECI is equal to ECX, ECI is bigger than the ECX, and then it will jump to a loop end. So after we do all of the loop until the end, it will go to a loop end, and then we want to record the end time. So we call the game m second, and then capture the end time, and then store into the capture end variable. And then we just calculate the elapsed time, means that we calculate the difference for the ending time and the starting time. So move the ending time to EAX, and then we compare the EAX with the starting time. If the starting time is bigger than the ending time, means that maybe we do this program at the midnight for 11:59 p.m. and then it's our starting time, and then our end time is 00:12 a.m. So our ending time must less than the starting time. So we want to prevent this occur. We want to simply add the time for the EAX so that it will make sure the ending time is always bigger than the starting time. And then later we subtract it if we don't get the negative value. So if the starting time is bigger than the ending time, we will add the EAX with this number. If the ending time is bigger than the starting time as usual, it will jump to the skip midnight, and then uh we subtract the capture start with the EAX, and then we put into a elapsed time, which is the time difference we put in the elapsed time variable. Later, we already have the elapsed time variable, we just display the result. We'll display the result, we'll store result message in the EAX, will display the result. Over here, we'll display the first starting time, we'll display the ending time, we'll display the elapsed time, which is the time difference, and then we display the sum. The last part, you actually want to prompt the user want to continue or not. If you want to continue, press Y. Don't want to continue, press another choice, and then we end the loop. So right now we want to show the process for the output. So first, the information will show her. So we choose the first is the 50 loop. So we just enter 50 loop. Make sure our computer is running. And then the first capture time is the in millisecond. We show here. The last, the ending time show here. And then the difference actually is the ending time minus the starting time. Forgot the difference. And this is the sound value. You want to continue. So and here we can see for the number of loop 50, our execution time is 1557. And then we do the next instruction. Let's say we do the 200. So the different execution time is the 6198 millisecond. Means that as we increase the number of loop, the execution time will increase also. So it is the directly proportional. If we choose the number of looping 700, we just wait a little bit slow. So the different execution time will become 21,000. So means that our loop when increase the loop, our execution time will increase also because the computer want to run more equation, they have the bigger workload for our computer. So that's all for this program. Thank you.